Hi, I am Ganesan and I have finished my Masters in Product Design and Manufacturing in Pondicherry University. Now we are going to discuss about the propelling nozzle. Now before going to the topic, we just know what are the properties of a nozzle as well as the function, classification and the types of nozzle. First, entering into it, what is the nozzle actually made for and what are the function of the nozzle? Nozzle is nothing but it uses the gases from the engine, which is exhaust gases from the engine, which helps us in increasing the velocity of the exhaust gas, which propels the jet in the opposite direction. This is the actual function of the nozzle. So that the nozzle helps us in improving. Nozzle helps us back pressure control to the engine, so that the engine attains a stable position over the control of the wheel, as well as it also acts as a accelerating device, which helps us in converting the thermal energy into kinetic energy. Now, some of the functions of the nozzle are being classified here with respect to their shapes as well as with respect to their design made for. We are now going to see what are the based on the design, how they are classified into. It is being classified into convergent as well as convergent divergent nozzle. When considering about the convergent nozzle, here it is convergent duct over here, so that the pressure as well as the mass of the exhaust gas over this area will be high, will be low, whereas when it is subjected to this duct, it will be at a higher velocity, so that the exhaust gas which will be emitted at a higher velocity, so that it gives a better thrust in order to increase the speed of the jet. Here, this kind of convergent nozzles are used in normal aircraft engine, it will be discussed later. Whereas convergent divergent nozzle, here when the exhaust gases reaches at this convergent area, after reaching here, it moves to the throat area, so that the exhaust gas are being consistent at this area, so that it gets a better velocity as well as a higher velocity, and the expansion is carried out over this area, which gives a better performance when compared to the convergent nozzle, so that we can get a better performance in this convergent nozzle when compared to the convergent divergent nozzle. This kind of convergent divergent nozzles are used in rocket engines, so that it requires very high speed as well as a very high thrust in order to move to a higher speed in order to reach its destination. Here we are now going to see about some of the classifications of the nozzle. Nozzles have been classified based on the speed of the sound with respect to, as well as with respect to the geometry of the nozzle, as well as with respect to the design. Now we are just going to see how it is being classified with respect to the sound. It has been classified with respect to the sound as subsonic, sonic, as well as supersonic. How we are calculating the nozzle with respect to the sound, in the sense we are just using the Mach number. Mach number is the velocity of the aircraft with respect to the atmosphere by the normal speed of the sound. Here, if subsonic uses a Mach number which is less than 1, as well as the sonic aircraft use Mach number which is equal to 1, and the supersonic uses Mach number which is greater than 1 within the value of 4, as well as hypersonic uses the Mach number which is greater than 4 to 8 or something like that. Then with respect to the speed, we are just calculating what are the design procedures we have to carry out in designing classification, when designing the nozzle. With respect to the geometry, there are two types of designing in the geometry, in the sense the fixed model as well as the variable model. In the fixed model, we are just going to design the nozzle with respect to the diameter which is fixed, so that we can't change the diameter of the nozzle with respect to the throat value also. This kind of nozzles are used in aeroplane as well as the subsonic jet, which we are using in our day-to-day life, whereas the variable nozzles are used in jet engines as well as in rocket and supersonic engines. So that the variable nozzle in the variable nozzle we can increase or decrease the diameter or the throat value diameter, so that with respect to the thrust only we are going to calculate what is the actual diameter of the nozzle, so that we are in a need to find out with respect to what amount of thrust we are just expecting in order to propel the aircraft. So in order to propel, with respect to that we are just deciding about the nozzle diameter as well as the throat diameter with respect to the variable geometry nozzle. Whereas with compared to the design, it is briefly described into convergent nozzle, divergent nozzle as well as convergent divergent nozzle. As we discussed earlier, convergent nozzle is usually a convergent duct over this area, so that the pressure and the gases which is available at this area will be at a low velocity, whereas when it comes into a closer area, whereas at this throat area it will be having a higher velocity when compared to this area, so that the propulsion of this thrust will be high at this area, which leads the propulsion of the aircraft at a higher speed. Whereas in the convergent divergent nozzle, here when the exhaust gases reaches at this area, here the throat value, with the help of the throat, the exhaust gases from the engine is consistent at this area, which is consistent at this area, so that when it reaches from a lesser velocity to a higher velocity, it just pulls with respect to the motion of Newton's third law of motion with equal action as opposite reaction in the sense with the higher speed. At this convergent area, the expansion process is carried out, so that the exhaust gases are coming out at a higher speed when compared to this also. These kinds of convergent divergent nozzles are usually used in rocket engines. Now we are going to deal about what are the types of nozzle which is available and which are being currently using with respect to the design as well as with respect to the geometry as well. The first we are going to deal with the ejector nozzle. Whereas the ejector nozzle, what kind of ejector nozzle are designed with respect to the subsonic speed. Based on the subsonic speed, they have been just classified, designed with respect to their speed, with the speed of the sound, so that we are just going using a better subsonic nozzle uses spring-loaded petals, so that we can get better emission in the sense better thrust over this nozzle in order to gain better performance of this engine. Here at the subsonic speed, when the gases are being exhaust at this area, when it reaches this area, the exhaust gases are ejected at a higher velocity, so that it will be consistent at this area in order to get a higher velocity. After consisting at this area, it expands over this area, so that the velocity of the exhaust gas will be high when compared to when compared to the inlet area of the nozzle, that is the convergent nozzle. Whereas the divergent nozzle, here at this area we can get a better velocity of the gas which is released by the engine. Whereas these kind of ejector nozzles are used in CSR 71 and F111. Here the next one is the IRIS nozzle. Here what is meant by IRIS nozzle in the sense, the full form of IRIS is intelligent rotation in space. Here this kind of nozzle uses hydraulic hydraulic pedal, so that it can be adjusted, the diameters or the design thrust value can be adjusted using these hydraulic pedals, so that we can, with respect to what are the thrusts which you are expecting, which can be obtained using IRS nozzle. These kind of nozzles are used in F14, F16 and B11. Then the next type of nozzle is rocket nozzle, where this kind of nozzle uses a fixed geometry, in the sense rocket are subjected to certain weights. With respect to their weight limitations, they have been subjected to a fixed geometry, so that we can get, since the rocket has to carry some other requirements of the in the sense based on the space only, they have been designed, so that the rocket nozzles are being designed with a fixed geometry nozzle. With respect to fixed geometry nozzle, we can get a higher thrust value. With respect to the thrust value, we can get a better propulsion. so that rocket nozzles are used in fixed geometry model. With respect to the fixed geometry model, rocket nozzle, these kind of rocket nozzles are used in F106. Then last one is the low ratio nozzle. These kind of nozzles are used in jet turbofans, whereas single craft engines, single craft aircraft, like that, they will be using a turbo ratio nozzle, so that the performance of the engine will be lesser when compared to this ejector nozzle, IRS nozzle, or rocket nozzle. Then what are the attributes we need to consider when we are designing a nozzle? Here some of the attributes which have been mentioned over here, in order to consider what are the parameters which we can consider to increase the efficiency or increase the thrust in order to get a better performance with respect to the dimension or the design of the nozzle. So just now we are going to find out what is the throat diameter. If we know the throat diameter, we can find out what is the exhaust velocity of the air which is flowing out at the end of the nozzle. With respect to the exhaust gases only, we are just finding out what is the actual diameter of the throat as well as the actual diameter of the nozzle as well. Here, first, the throat diameter is calculated with respect to the coefficient of discharge, whereas the coefficient of discharge is the ratio of actual, in the sense, coefficient of discharge is the actual value by the ideal mass flow rate. With respect to these, we are just calculating what is the actual flow area which is in need to get from the actual area available. With respect to the actual available area as well as the actual flow area, we are just calculating what is the exit area of the nozzle. With respect to these values, we are just calculating what is the throat diameter, which helps us in increasing the diameter of the throat as well as the diameter of the nozzle as well. Here, the next one we are going to consider about the determinant velocity coefficient. What is the velocity coefficient in the sense? Here, velocity coefficient can be calculated using actual exit velocity with respect to the ideal exit velocity. How we are going to calculate the velocity coefficient in the sense, with respect to with respect to the gas table, we are just we can find out what is the Mach number and what kind of speed it has to be traveled. With respect to the speed, we are just calculating the Mach number as well as the pressure ratio. Pressure ratio in the sense, it is the ratio of the ratio of the exit pressure at the nozzle with respect to the atmospheric pressure, that is the ambient pressure. If the exit pressure and the ambient pressure are equal, then we will be getting a better thrust when compared to three kinds of nozzles which I am going to discuss now. Here, this is three types of nozzle where we can get a better idea over what is the velocity flow over this area. In under expansion velocity process, here the gas from the engine flows above this area also, so that it is under expansion process of a nozzle. Here, this is the difference between what is the actual pressure ratio which is carried out. Here, which is the actual pressure ratio which is carried out over this area. Here, in the under expansion process, the exhaust gas which is released from this inlet, that is the conversion to diversion nozzle. Here, we will be getting here the atmospheric pressure is greater than that of the exit pressure, so that here the performance will be low. Whereas in the ambient pressure control, this is the ambient control, whereas the flow is within the whereas here the atmospheric pressure, that is the ambient pressure, is equal to the ambient pressure is equal to that of the exit pressure, so that we will be getting a better thrust over this area when compared to this one. Here, if the atmospheric pressure is higher at this area, so that there will be a throat deflection, as well as the throat will be less when compared to this one. Here it is a over expansion process. With respect to this only, we are just calculating what kind of thrust which we require for designing a nozzle, and what will be efficient for us to go for a nozzle design. Here, just we are going to design what is the determine the velocity coefficient with respect to this expansion process only. With respect to the velocity coefficient, we can calculate what is the actual exit velocity as well as the ideal velocity. With respect to this ideal and actual, we are just going to calculate what is the velocity coefficient. Now, how come we can calculate what is the actual exit velocity is now discussed using formula, that is V is equal to square root of T into R divided by M into 2 gamma divided by gamma minus 1 into 1 minus P by P power gamma minus 1 by gamma. Whereas T is the temperature, absolute temperature of the inlet gases at the nozzle, whereas R is the universal gas constant, where M is the molecular mass of the gas which is at the input of the nozzle or output of the nozzle. So then what is the lambda? Gamma is in the sense the isotropic expansion factor with respect to in the sense Cp by Cv value with respect to constant pressure, specific heat capacity of constant pressure and constant volume, and P is the exit pressure at the exit of the nozzle, and P is the ambient pressure which is available at the atmospheric pressure. With respect to this formula, we can calculate what is the actual velocity of the nozzle, and with respect to the actual velocity and the ideal velocity, we can find out what is the velocity coefficient of the nozzle, and we can find design with respect to which kind of what range of thrust we are needed. With respect to the thrust only, we are just calculating what is the diameter of the nozzle as well as the throat value. Then the next attribute which we are going to deal with the nozzle performance with performance and the assessment. Here we are just going to calculate what is the thrust coefficient. How we are going to find out what is the thrust coefficient in the sense. Here we are just going to deal with another formula, that is F is equal to m dot Be plus Pe minus P naught into A. Whereas thrust is calculated using this formula, where m is the molecular mass of the gas at the exit, as V is the exit velocity over the nozzle, and P is the exit pressure at the nozzle at the exit of the nozzle, and P naught is the ambient pressure which is available at the nozzle, which is available outside the nozzle, that is the atmospheric pressure, and area A is the area which is been used with respect to the thrust. Here, when we calculate with respect to if the ambient pressure which equals to the exit pressure, then we will be getting a better thrust. So that if thrust can be calculated using F is equal to m dot V equation, whereas m is the molecular mass of the gas which is being subjected to the nozzle, and V is the exit velocity of the gas which is being emitted. Then just using the thrust coefficient, we can find out what is the gross thrust, that in the sense the overall thrust which is available with respect to the thrust value.